Good afternoon, and thank you for joining us for our second Red Talks online webinar, The Role of Big Data, Artificial Intelligence, and Supercomputing in Fighting the Pandemic, as the second of our virtual version of Red Talks online series, RED standing for Research, Education, and Discovery. These webinars are led by Rensselaer researchers who highlight and discuss our approaches and solutions to today's global challenges. A few housekeeping items before we begin. Please make sure your volume is turned all the way up. You will be muted throughout the presentation out of respect for our presenters. You will see that there is a Q&A feature at the bottom of your screen. Please feel free to type in your questions, and we will get to them as time allows during the Q&A portion of the program. I am now pleased to introduce our host and moderator for today's discussion, Mr. John E. Kolb, PE, was a class of 1979. Mr. Kolb is the Vice President of Information Services and Technology and the Chief Information Officer at Rensselaer.
So thank you and welcome. And let me see if I can bring up our application slides. Should have it here in a second. And that should work. So welcome to the second online Red Talk. This is a Rensselaer Research, Education, and Discovery presentation. Our Red Talks epitomize research in the new Polytechnic and how it integrates with the education of our undergraduate and graduate students. As it was said, my name is John Kolb. I'm the Vice President of Information Services and Technology and Chief Information Officer here at Rensselaer, and I will be the moderator for this event. I want to thank all of you for joining this event. There's close to 200 people in the audience right now. I'm pleased that the 18th president of Rensselaer, Dr. Shirley Ann Jackson, is with us, and we will hear from her a bit later. I'm also happy to note that 4 of our trustees are also in the audience, including Judge Arthur J. Garza, class of 1962, Nancy S. Mueller, Curtis R. Preen, class of 1982, and Catherine Murtaugh, class of 1987. So overall, the research enterprise at Rensselaer comprises over 30 research centers, supporting graduate students and undergraduate researchers with over $100 million in annual expenditures. It is organized into 5 signature thrusts according to the Rensselaer Plan 2024. The signature thrusts align Rensselaer research with the most pressing global challenges facing humankind, such as human health, the environment, global warming, future energy resources, stewardship of critical materials such as food, water, and fuels, and physical and cyber security. To address these challenges, research at Rensselaer integrates the frontiers of engineering, basic sciences, computation, and data science, and cognitive and social sciences. This intellectual marriage provides innovative solutions to global challenges, including mitigating disease, providing clean food and water, developing new sources of clean and renewable energy, and establishing a resilient national and international infrastructure. We are inventing new methods for advancing manufacturing that lead to new products and processes. We are also developing new materials for advanced computing, energy storage, and medicine. We are pioneering new technologies to manage the explosion of data from new communication networks and control systems. And most urgently, right now, we are addressing the greatest challenge facing humankind for over a century, the COVID-19 pandemic. Rensselaer researchers from all 5 schools, the School of Engineering, Humanities, Arts, and Social Sciences, School of Science, the Lally School of Management and Architecture, are all at the forefront of the fight to mitigate the effects of the coronavirus and ultimately to defeat it. The efforts of Rensselaer researchers have received national headlines across a range of endeavors. Our first virtual Red Talk on April 28th, moderated by the VP of Research, Robert Hall, focused on the biological and biomedical research at Rensselaer that is addressing the coronavirus challenges head on. This second Red Talk will focus on data, artificial intelligence, and machine learning, and high-performance computing. At Rensselaer, we talk about the 4 Ps, that is, people, programs, platforms, and partnerships. Let me start by sharing a short video with our president, Dr. Shirley Ann Jackson, describing a major platform in this area which would not have been possible without strong partnerships with IBM and New York State.
We recently were awarded a $30 million grant from the SUNY Research Foundation to purchase a new supercomputer center. And this will be one of the top high-performance computing systems in the US and in the world. It will support research in AI itself and in fields across a broad intellectual front. We have begun a very exciting partnership with IBM, the Artificial Intelligence Research Collaboration, or the AIRC. It will lead to a major new research division at Rensselaer, as well as new academic programs, and a significant enhancement of our already magnificent computational ecosystem that will constitute the most advanced university-based testbed for artificial intelligence and deep learning in the world.
As the person most responsible for bringing this supercomputer to Rensselaer, it's great that she was able to introduce AiMOS and is able to join us today on the WebEx that we're doing right now. And so let me see if I can get us back to the screen, and let me introduce several of our leading people in this area to discuss some of the programs and projects in this area. Our panelists for today's discussion are Professor Christopher D. Carruthers. Professor Carruthers is a faculty member in the Computer Science Department at Rensselaer Polytechnic Institute. He received his PhD, MS, and BS from the Georgia Institute of Technology. Prior to joining Rensselaer in 1998, he was a research scientist at the Georgia Institute of Technology. His research interests are focused on massively parallel computing, which involve the creation of high-fidelity models of extreme scale networks and computer systems. These models have executed using nearly 2 million processing cores on the largest leadership class supercomputers in the world. We also have with us Professor James A. Hendler. Professor Hendler is the Titleist World Professor of Computer, Web, and Cognitive Sciences and Director of the Institute for Data Exploration and Applications, or what we like to call the Rensselaer IDEA. Jim is a distinguished researcher with over 450 books, papers, and articles. In addition to his academic work, Jim is also the former chief scientist of the Information Systems Office at the U.S. Defense Advanced Research Projects Agency, or DARPA, and he's been a consultant, among others, for DHS, NASA, Department of Energy, the White House, and New York State government. Jim is also the acting director of the AI research collaboration with IBM that Dr. Jackson mentioned in her video. So let's start off, Professor Carruthers. Maybe you could provide a bit more detail on AiMOS and what's so special about AiMOS? And if we can get Professor Carruthers off mute, we may be able to hear him.
Sorry, thank you. So thanks, John. So first, I want to just thank everybody for taking their time today and attending this Red Talk. It's exciting to be here and tell you more about AiMOS. So the first thing to let you know about AiMOS is one part of a much larger multi-billion-dollar hardware center here in New York State involving our key collaborator, IBM. In particular, this will serve as a test bed for testing out new AI hardware accelerators that are developed as part of this program. So taking a step back, though, when we think about supercomputers in particular, we think and really divide them up into their compute, their storage, and really their networking capabilities. So first off, if we look at the compute, one of the first things that we noticed about AiMOS is there is a really big departure in compute from our past systems. In particular, our past IBM BlueGene-L and BlueGene-Q systems. In particular, this system, unlike those previous systems, really use graphic processing units, or GPUs, as the lion's share for its compute. So AiMOS has something like 1,500 of these GPUs. Now, Rensselaer, of course, is not new to GPU technology. We have to give big thanks to RPI trustee and board member, as well as NVIDIA co-founder Curtis Preem for that. He invented, in fact, one of the first GPUs that were used in personal computers. Now, these GPUs, of course, do the lion's share of the compute, but we still need very fast, nimble CPUs to do the coordination and really conduct all of this other work that these GPUs are doing. That together brings together a really interesting compute ecosystem that we haven't seen before, and it turns out to be extremely fast. And sort of how fast is it? Well, if we look at the compute capacity of AiMOS, it equates to if every human being in the world, all 8 billion humans, they're able to do essentially 1 million calculations a second if we're looking at what AiMOS can do today. That is a lot of compute power. So we're talking about 8 billion million compute operations. But that's not all. So to bring this together, right, we need a storage system that can meet this demand. And so if we look, AiMOS now has or will have an 11 petabyte storage, big number. What does that really equate to? So it turns out that that if we looked at sort of capacity of such a storage system, it's about 80 copies of the entire Library of Congress, to put it in perspective. Now, the last part of this is the networking, and that's really the secret sauce that is AiMOS. So this networking is much higher speed than your home network or even in most data centers. Each one of AiMOS's 252 compute nodes can essentially deliver data at something like 25 gigabytes a second. In sum total, it's something like 6.3 terabytes a second. Or put it another way, we could basically remove the storage and put it back again of your entire hard drive for most people on this call in about a second or less. So that brings us to the last point, which is, well, where does AiMOS sort of rank in the world of supercomputers? And it's pretty impressive. Currently, right now, we're at 8.339 petaflops, which puts us at number 23 in the world on the top 500 list. And even probably more important is the power efficiency of the system. And we're actually the second most power efficient in the system in the world. Again, that's estimated based on our current numbers using the current list of the green 500. So indeed, John, these are really an impressive capabilities for our leadership class system that we have here.
That's great, Chris. And that was the system we brought online in November, December of 2019. But you just also brought on, if you will, a little brother or sister to AiMOS, and maybe you could describe that.
Absolutely. So this is our x86 GPUs. These are, instead of being IBM Power-based systems, these are Intel processor-based systems. And you're seeing the specifications there in front of you now. Essentially, it's a very similar architecture to AiMOS. One big departure, of course, these are air-cooled, not water-cooled. So we're anticipating the performance being a bit less on these systems in practice from what we're understanding, but we're still, of course, on a per node basis. But in terms of the aggregate performance of these systems, we're estimating that if we run the LinPack test, they'd come in around 1.6, 1.7 petaflops, which I'm saying that's small, but as we would point out, our last supercomputer, our Blue Gene Q, the previous AiMOS, actually was only about 1 petaflop, and I say only, which is very impressive in this day. So we're fielding a smaller system that's nearly twice as powerful as our previous system. So would be our second system, and interesting enough, it would come in a rank of around 240 or 250. Again, that's our estimate. But the big thing with both of these systems, and I really want to emphasize this to our attendees, is that both AiMOS and AiMOS X are open resources for the RPI research community. And again, this is really unique to Rensselaer. So that means all of the graduate students, faculty, and undergraduates, and I want to really emphasize that, undergraduates have access on AiMOS to conduct a wide variety of computational data analytics, as well as AI machine learning projects.
That's great, thanks. So Professor Hendler, why is what Chris just described so important? And in particular, how does AI fit into all of this?
So John, we'll be talking a little later about some other applications things, but I thought I would take this one And people looking on their screen will see just an eye chart, tons of little words on one side of the screen and a few pictures on the other. This is actually from a project that Professor Malik Magnan Ismail is doing here at Rensselaer. But what you see on the screen is a list of a whole lot of counties in the US. And for each of those counties, if you click on them, you would see this analysis that shows what is the predicted spike of when the pandemic is going to hit the most? What does it look like if we maintain social distancing? When could we start releasing social distancing, and what would that cause? But on this screen, you can see about 150, 200 different counties and countries. There are over 3,000 counties we want to run this for. And then where the AI really comes in is we'd like to be making comparisons. We'd like to be looking at all the different ways these different counties, which ones align with each other, what's been successful at one that might be applied somewhere else. Certainly what could be applied in a rural district may be very different than what could be applied in a urban district. And all of those things, just finding those kind of complex relationships among so many different things requires compute power way beyond what any of us have on our own machines. So just running the part you see on the screen here takes us a few minutes on a reasonably powerful computer. When we move it, we're in the process of porting this to AiMOS so that we can run every county in the United States multiple times a day, do those comparisons, start being able to let people actually ask what if scenarios. If we relax this, if we did that, would that change these numbers? So for decision makers, this kind of information is crucial. And we really need that kind of compute power we've been talking about to bring this kind of super local information into people's hands.
That's great, Jim. And how many counties did you say across the whole U.S.?
3,000 something. I forget the exact number.
That's great. Thank you. So one of the other activities we wanted to talk about, and Rensselaer has committed to, is something called the COVID-19 High Performance Computing Consortium. This consortium is bringing together the federal government, industry, and academic leaders to provide access to the world's most powerful high-performance computing resources in support of COVID-19 research. And let's run the video of the announcement of this consortium on March 22nd of this year.
Today, I'm also announcing the launch of a new public-private consortium organized by the White House, the Department of Energy, and IBM to unleash the power of American supercomputing resources to fight the Chinese virus. The following leaders from private industries, academia, and government will be contributing, and they're going to be contributing a lot of different things, but primarily computing resources to help researchers discover new treatments and vaccines. They'll be working along with NIH and all of the people that are working on this. But tremendous help from IBM, Amazon, Google, Microsoft, MIT, Rensselaer Polytechnic Institute, the Department of Energy's National Labor Laboratories, the National Science Foundation, and NASA. They're all contributing to this effort, and they're fully in gear.
So very exciting to have that announced at the White House on March 22nd. And we've been working very diligently on that. All three of us on this panel, myself, Jim, and Chris. And so, Chris, maybe you could talk a little bit about some of the specific projects that are supporting COVID-19 on this campus.
Sure, thanks, John. I'm happy to do so. So the first project actually is being led by Rensselaer computer science professor Dr. Gao, and along with Professor Wang from Northwestern. In particular, what they're looking at is they're trying to really understand how you can use cell phone data as part of figuring out contact tracing. And this is obviously very important in terms of understanding the impact of the spread of COVID-19. Although in their case, they're going to do simulations of this so they can do a lot of, as Jim was pointing out, with Malik's system how to do particular what-if scenarios, but this uses simulation-based approaches, and so we'll be using they will be using a lot of compute time to understand the impact of how we can use that smartphone data in a data privacy-preserving manner to figure out contacts. The next project is actually out of the Cleveland Clinic, and totally in a separate area. They're looking at drug repurposing methodologies. In particular, they're trying to quantify this interplay between sort of the virus-host interactions at the molecular scale and drug targets. In particular, they're doing a large number of molecular dynamics simulations using GROMACS, which is a very popular MD molecular dynamics tool that chemistry and bio folks like to use. And in fact, if we look, their usage probably in the last month, they've consumed almost 20% of AiMOS in doing some of those simulations. So a lot of work happening there. And then the next project from Harvard is analyzing this, the ability to triage scarce resources. In particular, we know that ventilators, for example, were a very scarce resource during and continuing during this pandemic. And so they're trying to figure out a way to create data-driven triage rules, but the normal approach to do this would be use what are called randomized controlled trials. To do that, it's not really timely or feasible given all the different options that they want to try out. In particular, they want to use and emulate these RCTs or randomized controlled trials over some 1 million different triage rule scenarios. So again, a very big compute problem, but one that AiMOS is very well tuned to tackle. But then in addition to that, and they're not really under the high performance consortium for COVID-19, but I want to just point out that just this past semester in parallel computing and programming, there were something like 10 students that decided to do COVID-19 spread modeling projects. And so they applied their knowledge from the course to kind of figure out how to maybe do this and do it very, very efficiently. And I can say they got, I think, some pretty good scaling results there.
That's great, Chris. And by the way, who's the professor for that parallel computing and programming course?
I am.
So they did good work, and I've heard that you can be tough in the classroom, so that's great. Thanks for sharing that. So Jim, maybe switch gears just a touch. You could talk a little bit about some of the future projects that you see in this area, and particularly the ones that you see developing at Rensselaer. And Jim, you may be on mute, so you may need to get off that.
Let me start with one that's a ongoing project and one which we will be working on very heavily this summer with a combination of professors, a few grad students, and a number of undergraduates all working remotely together. This is a project called COVID Minder. It was put together by, it's led by Professor Kristen Bennett of our math department. She's also in computer science. And what this does is, where the last one was sort of trying to predict things at the county level, this one really lets us explore how different kinds of aspects of COVID policy, COVID outcomes can vary throughout the US, and how to compare things across them. So we can see the trends, we can see the outcomes, we can see how things in parts of the country where you may have, for example, much higher diabetes, how does that impact things? So comorbidities, racial, social, economic factors, and then of course what governments are doing, what kind of resources they're investing, what kind of programs they're doing. Just to give you one example, the dark green line in the screen, for those who can see it, is Rensselaer County, where we're located. And what you can see is we're sort of in the middle of a curve compared to some of the counties down at the bottom of the slide, which are the ones that are mostly up northern New York and things like that. Whereas at the top of the slide, you see things like Westchester and New York City, which had much, much higher incidence. So it lets us compare these kind of things. So that's very useful as we're looking to see what is working, what is not working, how can we change things, et cetera. The next project I would mention is something that we're really just starting up. And this is kind of exciting because it's a real cooperation between the research side of the campus and the much more production-oriented side of the campus, which is run by John Kolb's organization. So contact tracing, which you've probably heard a lot about in the news these days, it is how do we identify and alert people who have come in contact with a person infected with the virus, or if we're trying to figure out who we need to look at, where things may have happened, how we find somebody who's has the virus and try to trace who they've met, where there may be outbreaks, things like that. Now, one of the problems with contact tracing is that it's very, very human intensive work. You have a lot of people, they do a lot of very long interviews and things like that. And so we have a campus team working to identify and evaluate some of the potential technologies for this, both from a sort of practicality and accuracy point of view, also with respect to handling privacy and security, both with respect to campus type issues and state and federal issues. And the idea is to build a system that can really help human contact tracers be much more effective, help decision makers know where they may need to put resources, change things. People in medical staffs can know where to be worried about something happening, or maybe imposing quarantines in certain areas, reducing activities. And then, on campus student life, it'll be important to know what's happening, things like that. So we've been looking at a number of different platforms actually from around the world. We're looking at what we have built into the infrastructure already on campus and what these new technologies can do to really build the kind of decision support systems that people will need to really understand how to deal with this disease.
And that's great. That's been a wonderful partnership so far. Okay, so that's the end of us providing a snapshot for folks. I wanted to point out a couple of URLs here. Back on the slide where we talked about the COVID-19 consortium, there is a link to the consortium website, and these slides will be made available, but you can go back and look at that. It's covid19-hbc-consortium.org. And in the bottom of this slide, there's a link to a podcast that Professor Carruthers and I did, has a little bit more detail with respect to AiMOS. So thank you, Chris, and thank you, Jim, for sharing your expertise and doing what you both do so well for our community and for the world. And let's see if we can open this up for some questions now. So we'll move this around a little bit so I can see the questions piece of things here. Chris, I was going to go back to what you said about the 8 petaflops and trying to put that in perspective. And maybe this is a touch before your time, sorry, Chris, but not before Jim's and my time. When we were both getting our degrees and so on, the ultimate system in the late 70s, early 80s was what they called a MIP workstation, a million instruction per second workstation, and that's what a lot of the companies were working on and so on. And what's just interesting nowadays is the way you described AiMOS. We could essentially have a MIP workstation per person in the world. So it's just amazing when you think about 3 or 4 decades, how far we've come. And your comment also about the 1.6, 1.7 petaflops being more than the Blue Gene Q. It's just amazing when you see that we've gone up several orders of magnitude from our first Blue Gene L, and now both of our systems are more than the last system, and so on. So the progression here is really great.
Yeah, absolutely. I was just going to add in there that if you look at one rack of Blue Gene L, right, it's been compressed down. That compute power in our one rack system has been compressed down to 1 GPU. In fact, that GPU is still 50% more powerful than one whole rack of Blue Gene L. So the scale of compression of compute is, even in the intervening since 2007 to now, has just been astounding.
Yeah. So a couple questions that are coming in. Oh, go ahead, Jim. Sorry.
No, I was just going to say the other thing that's really staggering is that Chris mentioned the amount of memory this thing has. I'm an all-timer like you, and I remember I once went to the largest disk farm in the entire world, which was within the federal government at that time, in an agency that remain nameless at the point. And it was the size of a football field with disk racks, things like that. Your cell phone has more memory now than that whole thing did. But AiMOS has so much. It's more than, thousands of times what the entire world had when we were learning. It's just phenomenal what we can do. Sorry.
No. There's some questions now. And first one is I think a short one, but it's a question, Jim, for COVID Minder. Is it publicly available and available for people to use?
Yeah, COVID Minder is available. In fact, there was a link on the slide that showed it, and it's also an open source project, meaning that people who'd like to get involved, including some of our alumni who've already actually been talking to us about it, will be able to actually download the code, play with it, extend it, et cetera. And as I said, it will be a very large project with a number of graduate students, undergraduates, faculty involved this summer.
That's great. There's a question from our Dean of Engineering, and Chris, this is probably for you. Can you talk a little bit more about the Power 9 architecture and what makes it so special?
Sure. The Power 9 architecture is really designed to be a very fast data moving architecture. In particular, AiMOS's actual original name, and when we were looking at it with IBM, it was called a data-centric system. And so what they viewed, and this was IBM's thinking at the time, is that data was at the center of everything. And that they knew, and this was coming out of research around exascale, is that data movement is what dominates the cost of delivering compute. It wasn't the compute itself. And so one of the things that, better than Intel, these IBM Power 9 chips can really move data back and forth. And that's very critical in terms of keeping up with what the GPUs are trying to do as well. Then the other piece to that is actually there's a unified memory architecture as well. And I know I'm getting a little nerdy and techie here, but that is one of the other centerpieces here that for those who did GPU programming prior to this system, you would move data from your host memory onto the GPU, do some compute and bring it back. And now you don't have to do that anymore. It's a unified shared memory space that you can just allocate memory once, and it can be at the GPU or the CPU, and it just works very seamlessly.
So a question in regard to contact tracing from our VP of Research. Does the computational power, storage, and bandwidth exist for automated nationwide contact tracing?
So at the moment, John, we should probably say there's a few different aspects of this and different kinds of contact tracing, and whether you're using geolocations or whether you're just using apps that let you know if you've come in contact with someone. The difference is some are centralized, some are decentralized. And at the moment, there certainly is enough power and bandwidth to do that at some level. Whether you're doing it for everybody all the time would be hard. But for the kind of level people need for contact tracing, that really doesn't seem to be where the biggest issues are. The issues that really are going to be the hardest ones to deal with are human issues. So somebody who doesn't want to be traced leaving their phone on their desk is not going to help us much. Geolocs have a lot of privacy and security issues. And so, in fact, the contact tracers we're looking at now are what are called privacy preserving. And I won't go geeky on you and talk about it for hours on end, but suffice to say that really paying attention to these issues are there. The bandwidth is there at a distributed level. Our ability to pull it together and then compute on all or some of this really is there now. And again, that's a lot of what we're trying to do with our experimental system that could then move it up to more production systems out in server farms and big companies and things like that.
So a great question beyond what we're doing today, and is after the COVID pandemic, where do you see the work being done with pandemic logistics being used? Can it be improved and be ready to be used in case of another pandemic? Can both of you answer that in 10 words or less?
Yeah, I think the answer is, first of all, we're learning a tremendous amount about the power of artificial intelligence for molecular modeling, for some of the network kind of things we do in tracing, which are also the basis of a lot of other applications. And for some of this predictive analytics I mentioned, figuring out what's going to happen in advance, all of those things have a number of business uses, including, of course, any future pandemic.
Yeah, there's a very good follow-on question here too. It's great that the data about individual U.S. counties can be tracked daily and potentially act for predictive future action. But are state and local authorities actually looking at this type of data and guiding their actions accordingly? Let you folks take a crack at that, and then I have a comment about that.
So I tend to try to avoid the politics and stay technical, but without this technology, they can't do it. With the technology, then at least within some parts of almost every state government, there are people who have this responsibility. How that gets played out at a political level is very different.
Right. And I one of the ways I would add on to that answer, Jim, is I think that's one of the great things about being part of this large consortium with companies like IBM and Microsoft and Google and Amazon, as well as other higher ed institutions, MIT, University of Texas, and others. It's large enough that it can have a longer term effect on where this all goes beyond COVID-19. And I'm hoping that the group will take that kind of look at this. There's a question here about will the contact tracking, tracing as described, be utilized by the broader campus community when Rensselaer does reopen? Let me take that one. What Jim described as some things that we're trying to work into production and be part of the solution to be able to inform decision makers as we think about reopening. And so that's why we're so focused on trying to get the researchers and the production folks working well together. Okay, so another one back to you, maybe to Chris. What makes AiMOS system particularly suited for drug repurposing studies and for COVID-19 and other diseases?
Sure. So most of the drug repurposing studies involve significant molecular dynamic simulations. We're seeing proposals asking for significant fractions of some of the largest systems in the world. And so then it's not just about, in fact, we have sort of a running joke at the CCI that if we just let the molecular dynamics folks have the whole system, they probably would take it. They can actually generate enough workload typically. So I think Jim was making an interesting point around really doing these types of studies, but doing them using some of these new AI techniques. So you're really taking advantage of every simulation run that you're doing and trying to be maybe a bit more predictive about it. In fact, we see a little that actually in the Cleveland Clinic project as well. And so then you can get your analysis done even quicker than you would by just brute force running all the simulations. It turns out AiMOS is very good at both of those. And where the sort of secret sauce is again, these graphic processing units, the GPUs, are well tuned for, of course, doing the AI and machine learning algorithms, as well as running molecular dynamic simulations.
So just to follow up to that too, there's another question here, Chris, I found interesting about what would be an example of data movement using AiMOS? I know that right now it's possible to move data into AiMOS, but it is not possible to access external system/move data externally without a specific process. Can you speak to that a bit?
Sure. So, well, first off, we'll tease that apart a bit, which is there's sort of two aspects to the question. When we typically talk data movement in the supercomputer, we're talking sort of at a lower level between, say, device like a GPU or CPU in the main memory of the system. But then you're right, there's also memory to storage as well. And so what you're sort of getting at here is some policies that we use at our facility that once you bring data in, there's no outgoing network connections externally. And that's just our own policy. But there are ways that we can do exceptions for that. In particular, in a secure way, we have the ability to have a proxy server in between. So we do allow external data sets to be brought in. And that's something that we're doing as well. But when we talk about the data movement and energy costs, we're really talking about from device to main memory, and that cost there, which is really a lion's share again of the energy cost that we see in these supercomputer systems. Great question, thank you.
And John, let me throw something in real quick, which is that, you know, a lot of what makes the power of having something like this so useful is that, so for example, with that one I talked about, the different counties, we're going out and we have 7 different scraping mechanisms, so ways of pulling that information because different counties report in different ways. We have 1 or 2 where we still haven't been able to automate it. We actually have to, you know, make phone calls and things to get some of the numbers. But once we can pull that information together, that gives us a repository that's very useful. In fact, the website for the Institute for Data Exploration Applications, idea.rpi.edu, if you go there, you can actually find 3 big buttons up top, one which takes you to COVID Minder, one which takes you to the predictive analytics I mentioned, and the third one actually takes you to a place where, as well as pulling in that information for our own computations, we are keeping a list of all sorts of resources with respect to useful data for people, useful computational techniques, challenges going on, et cetera. So one of the things we're trying to do for the Rensselaer community is really be a repository where you can find these kind of information and do your own projects as well as longer term things jointly with other people.
Yeah, Jim, just to build on that, there's another question here, which I think flows pretty well into your health analytics activity. Are telemedicine co-ops and businesses being utilized to assist with the contact tracing technologies? So you may want to talk a little bit about some of the work that your group has done in health analytics.
Sure. So we have another big project going on here is actually called Health Enablement by Analytics, Learning, and Semantics, which is a good acronym, HEALS, H-E-A-L-S. And really what we've been looking at there prior to the pandemic has been focused on how do we use information beyond just what's in the health record to help people make smart choices about life decisions, what to eat, how to exercise, things like that are really personalized right down to the level of the individual. And we're looking at some of that now with respect to also how can you do that in terms of these pandemics and things. But then more generally, a lot of these different organizations and things are really trying to figure out how to get a handle on these different aspects of computation, of artificial intelligence. How do we use these new technologies? And I think that's really where what HEALS is really about, is how do we integrate stuff from many, many different parts of the research community together. Many of the listeners will be familiar with the concept of the new polytechnic, which is Dr. Jackson's vision for Rensselaer, which really says it's working with people working across different disciplines and in many different ways. And I think this is a really great example. We have people involved in this project from the engineering side, the policy and social sciences side, computation, really pulling in people from a lot of different parts of the campus. And of course, the AI researchers trying to figure out how we put this together into things that can really change people's lives. And the pandemic has just made it much clearer, the urgency of doing that and the importance of the kind of work we do here.
So a question I have for both of you, because you both have been intimately involved with this COVID-19 high performance computing consortium. Can you talk a little bit about the reviewing of proposals, of what kind of proposals you're seeing, as well as this group that is called the matching group that takes those reviewed proposals and then figures out which computing resources in our country to use?
So I'll take the reviewing ones since I'm on the reviewing committee, and I'll let Chris do the matching ones since he's on the matching committee. So these proposals come in, they're fairly short proposals, very detailed, and they say, this is the research we want to do, this is the impact it will have on COVID, and this is the request we're making for computational resources. Those come in within a day or two. They are reviewed by 5 experts out of this group of about 30 or 40 of us. It's a rotating group. And we make recommendations of, low, high, or medium priority, or ask them to come back to improve the project, and then those go to the matching committee, where Chris can tell you what happened.
So at the matching committee, we get there. The committees. Fortunately, well, we don't review all the proposals. We only review the ones that are really sort of approved for getting an allocation. And then what we do is we sort of look and see, well, what are the requirements of a particular allocation request? Do they, for example, need x86 systems, and how much? Or can they run on AiMOS and make use significantly of GPUs, for example? So all of those factors come in. The other thing, we also look at, how big is this allocation request? Can we actually take it on? There's some allocation requests that have been pretty sizable, and probably something that maybe isn't really the best fit here, but there have been others, such as the projects we've selected, the Cleveland Clinic, the Harvard project, and of course our own Rensselaer Northwestern project that we mentioned. Those were all a very good fit for what we're doing. And then the last thing is really the technical fit as well, meaning can we really help enhance their project, make it perform better, and really provide good guidance, to really not just provide cycles. That's just not what we want to do. We want to become really a strategic partner for these project participants.
Yeah, I've been impressed being in some of these meetings that when you have something as focused as trying to work with COVID-19 and solve it, everybody puts aside a lot of other things to try to make things work. So that's fun to see. So a couple other questions here that are great. And Jim, this might be more for you, but are tools such as natural language processing being leveraged to learn from the vast scientific literature to accelerate the discovery of therapeutics and/or strategies for testing infected individuals?
That's a great question, John. We've been focused sort of on the data analytics part and things like that, but obviously on campus, there's a lot of other research happening relating to COVID, and a lot of people taking what they've been doing for other areas and bringing it to COVID, and this is a good example. So several organizations, in fact, one has been released by the Office of Science and Technology Policy out of the White House, working with various AI organizations, has been collecting these papers and making them available for researchers, because obviously one of the problems is if you want to get your hands on 19 million papers that have been written about molecules and coronaviruses, it's pretty hard to subscribe to everything and do it. So a lot of the publishers have agreed to make their work available, things like that. We on campus have at least 3 or 4 projects I know about. One is related to sort of question answering. So can we take all that data, pull it together into some kind of knowledge base so that people can then ask questions and not so much get just an answer to the question, more importantly, get something that says, this paper would help you answer that question, and maybe this way. We also have some more theoretical research that's starting to transition, which is to look at, here's a theory that I've been forming. Do what we're seeing, which papers out there would agree with me in a sense, and which ones would disagree? And that's not just based on a word-to-word comparison. So sometimes we have to know that this particular protein would have this particular interaction, which would cause this to increase. So if my belief is that something would cause that to decrease, then some other paper about that protein I would have to realize is in a sense disagrees with my theory, and I'd have to look at it to understand that. So we're doing a lot of that kind of work in a number of projects on campus.
So you can hear my clock chiming in the background. So another question here, which I really like, is are the simulations of randomized trials, such as those used in the Harvard resource allocation project you mentioned, considered just as statistically robust as real-life randomized control trials, or are there limitations to their conclusions? That's a great question. I don't know which one of you wants to take that one.
Chris does.
Thanks, Jim. So I can say the reviewers of that proposal very much thought it was a very important thing to be doing. And so a lot of folks looked at it from that perspective. And I believe the answer is yes, it's going to be statistically robust, but there probably are going to be limitations. At this point, we don't know yet. I can say the team of experts from Harvard, and there's also one person from IBM as well on the project who came out of the Harvard program. They're all very much looking at this, and they have expertise in this particular area in terms of ensuring the statistical robustness of these simulations. So it probably, like all of these types of things, it won't be perfect. They're going to be dealing with real human data, and there's always a lot of, I guess, noise in such data, and so that'll be a part of it. But we're very hopeful, as you know, in terms of us reviewing this proposal, that there'll be some really significant outcomes.
Yeah, I would just throw in one last gloss on that, which is the what a lot of the AI does, including in this work or these simulations, we can try a million different things. And what it can say is, here's 3 or 4 of them that look very promising, which could then be taken to much more robust human trials and things like that, where that would be impossible to run a million actual trials. So one of the things that's becoming more and more a paradigm, and looks like it may well become the future of a lot of medical research and be absolutely necessary for this vaccine. Some of the projects we're seeing in the HPC consortium include things like trying thousands of potential proteins interacting with thousands of other proteins at a molecular level that, again, before we had these computational resources, we'd be lucky to run a very small number of these. Now we can do these much larger things. But again, it's not to replace the human researcher. It's to be able to come to folks like, John and Deepak, who gave the last Red Talk, and say, here's some very promising possibilities. Can you use the traditional tools of biochemistry and biomedicine to help us, take them to the next level? Or those researchers can come and say, here's some stuff we've been working on. What are the chances that it's really going to have high impact? So it's a whole new way of working between the sort of computational side and the lab side that many people think is going to be absolutely crucial for the future of this kind of work.
That's great. So maybe to wrap up here a little bit, let me ask the two of you to maybe talk a little bit of the future of, and I'll separate this out, Chris, of where you think supercomputing is going from here, and not necessarily with COVID-19, but you can certainly use that as a launch pad of where we're going with supercomputing. And Jim, I'll give you a little bit of heads up. Where are we going with some of the data, AI, machine learning pieces here too, and over the next 5-10 years of our research and where the world is going. So, Chris, first to you.
All right. Thanks, John. So great question. So one of the great things about AiMOS is, if I look at its architecture, again, just data-centric, GPU-centric architecture, that looks like it's going to continue for some period of time. It looks pretty much the GPUs are going to win sort of the power compute efficiency battle. And so that's a good way to go. In fact, if we look at the next systems in line, in particular Aurora, which will be at Argonne National Labs in Chicago, that actually has the same number of GPUs. It's 6 GPUs and 2 very powerful CPU processors. So its core node looks very similar to AiMOS. The software stacks and things like that may change, but the underlying compute is going to remain the same. I think one of the interesting things in all of this is the bringing together then of supercomputing, and then beginning to make the supercomputer and cloud technologies come together in a nice way. We actually, even on AiMOS today, we have the desire to run Docker container images and schedule them through almost like HPC jobs. And so I think we're going to continue to see that capability. I know the data analytics folks would love to have these Docker capabilities and not have to run on bare metal. But we still need to continue to support our GROMACS jobs, because obviously looking at COVID-19, we still need to be able to do these molecular dynamic simulations for COVID and other viruses that may come down the road. So I think it's really going to be interesting in terms of the software ecosystem. There's a lot of work to be done there, but AiMOS is definitely on sort of the exascale path of systems of the future.
And John, what I would say about the future of AI is, and again, I'll try to keep this short. I do teach a summer course called AI in Fiction and Fact, and really I'm trying to help the students learn to tell the difference between what's real and what's sort of in the science fiction realm. But we've seen real breakthroughs in this technology in the past few years coming out of, you'll hear terms like deep learning and things like that. A lot of what's starting to happen now in AI is bringing together some of these newer techniques, some of the older techniques, trying to really figure out how we're going to hit big things. But I'd say there's really three main themes that I see, and this pandemic has been a great place, and this talk today has shown you several of them. So one is sort of this predictive analytics. So again, given a little bit of information about what we know now, how well can we predict what's likely to happen in the future? Who's more at risk of something and things like that? And we're seeing tremendous strides in that area. The project I talked about today is one really great example. Another thing we're seeing is traditionally data has lived in these nice square boxes. Think of an Excel spreadsheet or a traditional database table. But more and more, the stuff we want to do, such as in contact tracing, lives in these big network graphs. And so learning how to handle and manipulate those graphs in a computational way takes a lot of the supercomputing. Learning how to really understand what they're telling us, what impact they have, things like that, has become a major part of AI and something we're very involved in. But honestly, John, I think the most exciting part about all of this is none of this technology means anything unless it changes how people live, and preferably in a good way. So we're really looking, in the Cognitive Immersive Systems Lab here at Rensselaer is one of the top places this goes on, at just how humans and AI can better interact, how we get human in the loop, how AI can help us make better decisions, because it really should be the humans who are making the decisions most of the time, and the AI is helping us understand what are the implications of different aspects of those decisions and things like that. So it's a very exciting time to be an AI researcher, and having the right kind of tools like we have here at Rensselaer, along with this kind of ability to bring together people from many different parts of the campus to handle, again, the math of these analytics, the optimization and engineering, the social and political aspects, and of course the human computer interactions, just makes RPI a wonderful place to work on this.
Yeah, Jim, I absolutely agree. And I just have this image of being in CISL with these multiple cognitive agents working on doing the things you just talked about, reducing the literature searches or other things down, and then calling out to AiMOS to say, okay, here's the simulation I'd like to run, and so on, and all from sort of one place, and being able to do that and do that at scale. And that's really a lot of what we're talking about, is how do you really do it at scale? You mentioned 3,000 counties, and how do you at your fingertips say, okay, I'd really like to understand all 3,000 at the same time and put that together, and so on. So it is a great time to be doing this, and we have a lot of the right people, programs, platforms, and partnerships to do that here. So I'd like to conclude our time and like to thank the audience. I know we got started a little bit late, but this has been great. And thank you for your not only being with us, but some great questions. And to our speakers, Jim Hendler and Chris Carruthers, you did just a great, excellent job at not only sharing your expertise, but personifying the excitement and passion and brilliance that I think really define Rensselaer. So thank you to the two of you, and thank you all. And that's the end of our time together today. Thanks.
And thank you, John.
Thank you, John.
Well, great. Thank you. Thank you very much to all the panelists for their time today. And thank you to all the attendees for joining us today on this webinar. You'll be receiving an email in the next 48 hours with today's recording, along with a brief survey asking for your feedback. Be sure to check your email and social media moving forward for future Red Talks online. Please save the date for 2R Pi Day on June 28th, a virtual event where we can support our institute and stay engaged with our community online. More details and information coming soon. And we've also established a research fund that you can support at Rensselaer. It's supporting research at Rensselaer, as well as other areas, the annual fund and a student relief fund and many more. So please visit giving.rpi.edu for more information about this fund and other ways you can support Rensselaer. Thank you, stay safe and healthy, and have a great afternoon.